Good morning. So today is Thursday, February 25th, and we are going to be covering Le Chatelier's principle today. For our homework tonight, you guys will have the 5.13 homework. So our goals for today are to observe Le Chatelier's principle at work in a reversible biochemical reaction and to use Le Chatelier's principle to predict changes in equilibrium under a variety of conditions. In our overall mastery map, we are going to talk about chemical reactions when they're in chemical equilibrium, which we covered in yesterday's lesson. So if you did not have a chance to watch that, definitely go back and watch the recording. And today we're going to talk about how chemical equilibrium can be affected by change in conditions, and we can predict what will happen with equilibrium using Le Chatelier's principle. So just to review from yesterday, we learned that some reactions are reversible, so you can start out with A plus B and you can get the products of C plus D, but sometimes those products will go back and turn back into reactants. That's all reversible means. It means that the reaction can proceed in both directions. So molecules A and B can react to form products C and D, and if the conditions are just right, C and D can actually go back and reform A and B. And these processes will occur continuously and simultaneously. So while some of your A plus B is turning into C plus D, some of your C plus D will be turning back into A plus B. And we saw that yesterday whenever we were just looking at A going to B and B going back to A. And you guys could see some of the little molecules of B turning back into A. In terms of their rate in the forward reaction, so A and B are used at the same rate that C and D are formed. And then if you go in the reverse reaction, C and D are used up in the same rate that A and B are formed. And that's because A and B are turning into C and D are turning back into A and B, so that's why their rates are the same. Now, whenever the rate of the forward reaction is equal to the rate of the reverse reaction, that's when they're at equilibrium. So when the forward reaction and the reverse reaction have the same rate, that's equilibrium. So let's talk a little bit about Le Chatelier's principle. Le Chatelier, I always pronounce it wrong. I'm not French, so I don't have the not pronouncing the R down yet, but yeah, it's Le Chatelier. Sorry about that. So for all reversible reactions at equilibrium, anytime you have a change in the system, this will cause the reaction to move in a direction to offset that change. So let's look at what that looks like. So let's say we're going about our reaction goes to equilibrium, and let's say we add more of the reactants, so we add more A and B. Well, if we do that, our equilibrium is going to shift to the right. So it's going to shift this way so that we make more products. So this is how you would visually represent that. You draw a big arrow going to C plus D and a little arrow going to A plus B. So if we add in more reactants to get back to equilibrium, those reactants are going to be turned into more products. So you'll end up making more products. Now let's say you do just the opposite of that. So you remove some of each reactant. In that case, your equilibrium is going to shift the other way, so more of your products will be converted back to reactants. If you add more products, that's going to shift your equilibrium to the left. So if we add more of C plus D, that's going to make more of A plus B. And then if we remove some of each product, so if we take away some of our products, that's going to cause more of our reactants to turn back into products, and it's going to shift our equilibrium to the right. So let's talk a little bit about the equilibrium of breathing. So each time you take a breath, oxygen gas travels into your lungs from the atmosphere and binds to a protein called hemoglobin. This is hemoglobin right here. It's composed of 4 subunits. And in each of those subunits, you have an iron-containing heme molecule. That's the molecule that actually binds oxygen gas. And this reaction is reversible. So if you are at, so that just means that you can have heme right here. So HB is heme or hemoglobin. and you can have oxygen that's not connected in, or you could have oxygen that's bound to your hemoglobin. So, like I said on the previous slide, the binding of hemoglobin to oxygen is a reversible reaction, meaning that you can bind oxygen to hemoglobin or you can have it in its unbound form. And so hemoglobin is found in red blood cells, and it transports oxygen to various areas of the body, and in order to move that oxygen, it has to be able to bind it and then later release it. So that's why it's considered to be reversible, because here sometimes it's unbound, sometimes it's bound, so it can go either way. So it can go from hemoglobin plus oxygen to hemoglobin bound to oxygen, or it could go from hemoglobin bound to oxygen back to hemoglobin and oxygen. So what it'll do, it'll actually release the oxygen in areas of need. So it's going to bind it in high oxygen areas, so areas where you have a lot of oxygen, and then it's going to release it where you need oxygen, so in low areas of oxygen. So what you should do now is click on the link and watch the short video on binding hemoglobin. Okay, so we have officially mastered our first goal. We observed Le Chatelier's principle at work in a reversible biochemical reaction. We got to see that with hemoglobin binding oxygen. Now we're going to use Le Chatelier's principle to predict changes in equilibrium under a variety of conditions. So let's consider this right here. So consider the following reaction at equilibrium in a variety of scenarios. So let's say, for example, we have A plus B yields C plus D, and C plus D can go back and yield A plus B. Now, if we add reactant A to this reactant, if we add A, what do you guys think is going to happen? Good, so you should have said it will cause more products to form. So if we add more of our reactants, that means our reactants are sort of off balance in our equilibrium. We have too many of them, so they're going to be converted to products. So this will shift equilibrium to the right. Now for this same reaction, if we remove reactant A, what if we take reactant A out? Well, not all of A, but if we remove some of reactant A, what will happen? So if we remove reactant A, it's actually going to cause fewer products, and this will shift equilibrium to the left. So you'll make more of the reactants. Now what will happen if we remove product D? So if we remove some of product D from this reaction, we're going to end up with too many reactants, and that's going to cause more products to form. So that'll cause more products to form, and that'll shift our equilibrium to the right. And what if we add product D? So if we add product D, that's going to cause too many products, and we're going to have to make more reactants. And that will shift our equilibrium to the left. So that's how Le Chatelier's principle works. So there are several other reasons for shifting equilibrium. So for example, we have been talking about changes in concentration of products or reactants. So changes in concentration of products or reactants will shift equilibrium. But so will changes in temperature and pressure. So changes in temperature and pressure will actually shift our equilibrium as well. So if we have a temperature increase or a decrease, or a pressure increase or decrease, that will shift our equilibrium. Okay, so we observe Le Chatelier's principle at work in a reversible biochemical reaction, and we use Le Chatelier's principle to predict changes in equilibrium under a variety of conditions. So what you guys want to do now is go ahead and do the 5.13 homework on Le Chatelier's principle. And tomorrow we are going to review for the Unit 5 test. Monday we'll take the test, and then we'll move on to stoichiometry.